So now that we know how to take derivatives of inverse functions, we're actually going to want to take derivatives of inverse trig functions. And since I know not everybody has seen inverse trig functions, I thought we could do a very, very quick review on inverse trig functions. So let's get started with that. So remember the way inverses work. You start with a function, and you want to form the inverse. Why? Well, the inverse is the opposite function. It tells you which input for the original function gives you the output you're plugging in. So like with x squared and square root of x, for x squared, if we want to know what gives us 4, the square root of 4 tells us what does, which is 2. And so the inverse function answers, what do I need to plug into the original to get this thing? Right? And log and exponential are inverses too. Why? Well, log base 3 of 81 is 4, because it's the answer to 3 to the what is 81. So what about trig functions? How do we take the inverses of trig functions? Like, for example, what's the inverse of sine or cosine or tangent? Well, it turns out that they are what we say they are, and here's how we get them. So it's important to remember that when we say x squared and the square root of x are inverses, that there's a lie going on. It's not totally true. The square root of x is a parabola, but I'm sorry, x squared is a parabola, but the square root of x is not a parabola, right? And so they're not totally inverses. What we have to do is we have to add the extra condition that x is greater than or equal to 0. Then x squared and radical x are inverses, right? Look at the graph of x squared in yellow there. That's not 1 to 1. However, when we restrict the domain and we cut off all the negative numbers as being possible inputs, we do get a function which is 1 to 1. And so for f of x to have an inverse, f has to be 1 to 1, or we must restrict the domain so that it becomes 1 to 1. And we should know that the graphs of our trig functions are super not 1 to 1. They're periodic. They happen a lot to 1. So to figure out what is sine inverse of x, look at the graph of sine x. That's not 1 to 1. But if we go ahead and restrict it to just values between negative pi over 2 and pi over 2, the red part, it becomes 1 to 1. So once we make it 1 to 1 by restricting the inputs, we can make an inverse. We would say that sine inverse of x is y is equivalent to sine of y equals x. And the only possible values of y we're going to allow are those between negative pi over 2 and pi over 2. So for example, sine inverse of 0 is 0. Why? Because sine of 0 is 0. And sine inverse of 1/2 is pi over 6. Why? Because sine of pi over 6 is a half. Even though sine of 2 pi is 0, sine inverse of 0 isn't 2 pi. Remember, we've restricted the possible answers, right? They have to be between negative pi over 2 and pi over 2. And so when we try to take arcsine of 0, we only get 0, not any of the other ones that would give us 0. So let me give you some facts about sine inverse. 1. Sine inverse has values of x between negative 1 and 1 as its domain. Why would that be the case? Well, if you look at the previous slide, sine can make values between negative 1 and 1. That means the inverse can take values between negative 1 and 1. So that's the first thing, that domain and range become switched. Well, what about the range? Well, sine inverse can make values of y between negative pi over 2 and pi over 2. So when you think about a function, you think about the types of things it eats and the types of things it spits out. Sine normally eats an angle and tells you a number. So what happens is sine inverse has the reverse diet. It eats real numbers and spits out angles. So whenever you see sine inverse of x, you should think, oh, that's an angle. And here's a graph. If you graph sine of x, which is in the light orange, then you flip it over y equals x to get the graph of sine inverse. graph of sine inverse almost looks like x cubed, right? It's increasing and then flat and then increasing again. So there's the graph of sine inverse. So we're going to move a little bit faster through the rest of the trig functions here. Cosine inverse, well, if you graph cosine, you can see that we have a problem. We have to the left and to the right the same values. And so what we do is we restrict ourselves to just values of x between 0 and pi. If we do that, we get all possible values for cosine, and we don't have a function which is not one-to-one. We only have a one-to-one function. And so the definition is cosine of x equals y, if and only if cosine of y equals x, for values of y between 0 and pi. For example, inverse cosine of 0 is pi over 2, since cosine of pi over 2 is 0, and inverse cosine of 1 is 0, since cosine of 0 is 1. And then here's a graph of inverse cosine. Alright, so now the quickest part. Tan inverse. If we restrict here, we have a function which is 1-to-1. And so we only want values of y between negative pi over 2 and pi over 2. Since tangent, look at tangent, there's those two vertical asymptotes, right? As we get closer to each of those asymptotes, we get as big as we want. And so tangent actually makes all possible values, right? There's an angle, for any number you want to make, there's an angle which gives you that, right? So tan inverse actually can eat all possible values. Those two vertical asymptotes actually become horizontal asymptotes in the graph of tan inverse. For example, tan inverse of radical 3, well, that's just pi over 3. Why? Tangent of pi over 3 is radical 3. Now, this is the even shortest part of the video. We're going to do cosecant, secant, and cotangent. We're going to do the inverses for those three all at the same time. So cosecant and secant have graphs which don't make values between -1 and 1. So the domain of arc cosecant and arc secant is stuff less than -1 or bigger than +1. Right? Remember, what secant makes, arc secant eats. What cosecant makes, arc cosecant eats. And there we have the ranges for those. And cotangent and tangent are very similar. Cotangent can eat every value. Arc cotangent can eat every value because cotangent can make every value. And we just restrict the domain to be between 0 and pi. And so here are the three graphs of arc cosecant, arc secant, and arc cotangent. And that's it. So this is just supposed to be a refresher. Go back through, understand what's going on, and realize that domain restriction makes inverses possible. Go ahead and do the homework, and I'll see you next video.